Whoops. Right, so maybe I should go back. So here's I got it, great. So here's the agenda for today. First a review and then some new results. And I guess I have to apologize to Nam because I think he's heard me give the review part of this talk at his place once. So as thank you for the introduction. As you said, we're going to learn some economics maybe today. So I'm going to talk about a problem of asymmetric information. And this has various different possible economic applications, but the one that I find easiest to think about is the so-called monopolist's problem or nonlinear pricing problem. And so the idea is that you should imagine that you're going to go into business producing something, let's say automobiles, and you're going to market them to a field of potential buyers, potential consumers, and you would like to design a line of vehicles and a price menu for these vehicles to maximize your profits. So in this model, what is a automobile? I'm not sure exactly, but it's parameterized by things like its fuel efficiency, its comfort, its safety, its performance, maybe the number of passengers it can take, the range it can go without refilling, and so on. Maybe the technology, whether it's electric or gas or diesel, and or hybrid. So an automobile might be a point in like a 6-dimensional space. And what is a consumer? I'm not exactly sure of that either, but consumers are parameterized by things like their wealth and their income and the size of their family and how risk averse they are and maybe their age and how much they like cars. So a consumer might also be a point in a 6 or 7-dimensional space. And so I'm gonna model this situation by thinking of the automobiles as lying in some subset of n-dimensional Euclidean space. Sorry, you can't see that, and called Y, and the consumers as living in a subset X of a space possibly of different dimension M. And then there's also going to be a price that the vehicle trades for, Z. And as monopolist, you've done a bunch of market research. And so the value of car Y to agent X at price Z. And so that's all going to be encoded in a function G, which is sometimes called the direct utility, because that's somehow the value to agent X of the car price pair YZ. And you also have a probability measure mu on the space of potential buyers that measures the relative frequency of a buyer type X as compared to X prime in the population. And as the monopolist, you know the value to you of selling car Y to agent X at price Z. And so the freedom you have is to choose a price menu, which is sort of a map from the space of cars to the space of prices. And you like to choose this to maximize your profits, where the profits are basically given, they're the integral against, okay, so this is what's sometimes called a bi-level optimization problem. So each agent has their own variational problem, and your profits depend on what they do, their solution to their variational problem. And so agent X's problem is to choose that car Y, which maximizes the value to him if he pays price V for it. And then your profit is going to depend on which each agent X did. So it will depend on the identity of the agent, the car they chose, and how much they paid for it. And so that's the function you want, the functional you want to maximize. And the constraint in this problem is that if you raise your prices too much, some of the agents will just choose not to buy a car at all. So there's always, the agents have the option not to participate. And I'm going to model that by saying that, let's say the 0 car, you're forced to charge price 0 for. And so the agents can always choose the 0 car if they don't like anything that you're offering, the prices you're offering it for better. Okay, so this is the maximization problem that we want to study. And okay, so this is a little bit of a depressing theory because this is the theory that explains why airlines have an incentive to want to make economy class sufficiently uncomfortable that people who can afford to buy a business class seat or are traveling on the company's bill are strongly incentivized to prefer the business class seat. And another depressing aspect of it is that in this kind of theory, what you pay for something doesn't depend at all on how much it costs the manufacturer, the monopolist to manufacture it. It depends only on what the market will bear. And this also was supposed to explain airline ticket pricing. So back in the day, it used to be the case that if you bought it, most of us can remember, or many of us can remember a time when if you bought an airline ticket that included a Saturday night stay, it was less expensive than one that didn't. And this is because, you know, the presumption was that business travelers want to be home with their families on the weekend. And so you charge a premium for a ticket that doesn't include the weekend because you assume that the company or the business traveler is willing to pay more for it. But you don't want to exclude the leisure traveler from your flight service, so that you also want to offer cheaper tickets to people that aren't traveling on the company bill. But you don't know who, when they come to buy an airline ticket for you, you don't know whether the person's a business traveler or a pleasure traveler. So you try to differentiate the products to force them to reveal. That's the asymmetric information aspect of this problem. And asymmetric information used to be a very hot topic in economics. It's a little bit less relevant now that Amazon and Google know almost everything there is to know about each of us, that maybe there's no asymmetric information anymore. But on the other hand, it's still the case that, for example, you might not, for example, health insurance providers aren't allowed to discriminate based on, say, pre-existing conditions. So there might be regulations that even if they know your private information, they might not be able to take it into account in their price menus. So that's another kind of application. And in that application, the monopolist profit would depend strongly on the identity of the agent and not only the product and price that they sell them. And in a lot of the literature, this function separates into a function of the agent type and the product type, and what they pay enters linearly. That's sometimes called the quasi-linear model. But in fact, so part of the work that I want to describe is how to handle the case where the sensitivity to price can be nonlinear and can depend on the identity of who's buying and so on. And in the original economic applications of these asymmetric information problem, which date back about 50 years, were to optimal tax theory and educational signaling. And both of these were worked out in a one-dimensional context where basically the product has only one parameter, which is, say, quality, and the consumer has only one parameter, which is, say, wealth. And that, of course, simplifies things considerably. But again, it's a little bit of a depressing theory because Mike Spence and Jim Release shared a Nobel Prize for this work about 25 years later in the mid-90s. But in Spence's theory of educational signaling, the value of employers may be willing to pay a salary premium for someone with a PhD, but it's not because the employer thinks that during the course of doing the PhD, the worker learned something that might be of value to the employee. The idea is that the PhD is just a signal that shows that the person is maybe smart and able to learn. And so if they weren't smart and able to learn, they wouldn't have done a PhD. You don't actually care about the knowledge they acquired doing it, but what you care about is whether they're smart and able to learn. And so that's why you pay the premium for the PhD. Okay, so, and here's I have a slide devoted to the history of this problem. So Merlis and Spence worked on this one-dimensional case, and their basic observation was that when the benefit function, the mixed partial derivatives of the benefit function have a sign, then that will force the product consumed to be a monotone function of the type of the agent. And once you know that the map y from x to y, from agent to product is monotone, you can kind of reduce the whole thing to an ordinary differential equation with appropriate boundary conditions. And then about 25 years later, Rocher and Chenet published an influential econometrica paper in which they extended this theory to higher dimensions, but assuming the space of agents and products were the same, and that the surplus function depended in a bilinear way on the identity of the agent and the type of product consumed. So, this like Y1 would be the first kind of parameter of the automobile, and X1 would be how much does an agent care about that parameter, and Y2 would be the second parameter, and X2 would measure how much agent X cares about the second parameter, and these things would enter in an additively separable way. And the basic observation of Rocher and Chenet was that in this higher dimensional problem, the analog of being a non-decreasing map from the line to itself is that the product selected is going to depend on the price by being a convex gradient. So V star is going to be my notation for convex dual function. So you look at the convex dual function of the price menu V, and the derivative, the gradient of that convex dual function tells you what product agent type X is consuming. And there's a famous example in their paper, which is going to play a role in, especially in the second half of the talk, where they took the monopolist's profits to be basically their revenue minus their costs, and they assumed the cost was quadratic in the parameters the car produced. And they also, they had a particular example where they assumed that the types of the agents were uniformly distributed over a unit square. And then they observed the following phenomena. They observed that the convex function, which maps the type of the agent to the product consumed, the Hessian of that convex function can have rank 0, 1, or 2. And the space of agents divides into 3 regions, 1, 0, 1, and 2, depending on that rank. So these are the, up here in region 2 are the people who are either the wealthiest or care the most about having an automobile. And there, the convex function is uniformly convex. And so its gradient map is sort of locally a homeomorphism, or maybe even a diffeomorphism. And so these people, each agent here gets a customized vehicle customized to their preferences. Down here at the bottom of the market, the people who are, say, the least wealthy or care the least about having an automobile are just not going to buy a car. So even before Spence and Merle's, Armstrong in the early 1990s had observed that if you move beyond 1 dimension, if you're in 2 or higher dimensions, then if everybody's buying a car, then the monopolist has not raised prices high enough to maximize his profits. He has to price a positive fraction of agents out of the market in order to maximize his profits. And so that positive fraction of agents will live down here on the set omega 0, where the convex function is actually 0 and its gradient is 0. So all of these agents consume the null product. And then in between, there was a non-zero fraction of agents lie in this region where the convex function's Hessian has rank 1. And so the convex function is constant, say, along these lines, but it's strictly convex across the lines. And all the agents on one of these lines are going to consume a vehicle on the diagonal, which is sort of a compromise model between the two, let's say, fuel efficiency and comfort, the 2 parameters, whatever they are, or quality and reliability. And so, so this is like the ISO choice curve here. These anti-diagonal lines, all of those agents get the same vehicle. And so they called this bunching, and they thought it was very economically interesting. So the space of products consumed, which is something that the monopolist decides as part of their maximization problem. If you look at the measure of products consumed, it has a Dirac sitting at the origin. It has a portion that's absolutely continuous with respect to one-dimensional Hausdorff measure on the diagonal, and then it has a portion which is absolutely continuous with respect to 2-dimensional Lebesgue measure. And it was not clear at the time they wrote this in 1998 whether this bunching was a robust phenomena. How does it, or is it very sensitive to the particular choices they made in their model? And so that, in some sense, is one of the questions that some of this work addresses. So, right. Are there, maybe before I leave this, are there questions at this point? I wonder if I can put this in a more convenient place. So Guillaume Carlier wrote his PhD thesis on this problem in 1998. He was a student of Ibar Eklund. And one of the things he showed was that in the Rocher and Chenet problem, the map from agents to automobiles is continuous. And there's an unpublished work of Caffarelli and Lyons that shows it's actually Lipschitz continuous. And Carlier was also able to generalize the existence results to arbitrary functions of agent type and automobile, provided the model's linear and the price paid. And so one of my PhD students 10 years ago or so was able to extend this continuity result of Carlier's to these more general models, provided B satisfies some differential geometric conditions that I'm going to describe a little later in the talk. But so the way this works is that, of course, agent type X wants to maximize the value of the car Y he buys minus whatever he has to pay for it. And so this function here, which depends on B and V, I'm going to call the B transform of V, and that's also the indirect utility. And in order to get his existence result, what Carlier did was reformulate, instead of thinking of the principal's profits as being a functional of V, you think of them as being a functional of U. And in the case where B is bilinear, then this maximum is going to be a convex function. So that was what we saw in Roche and Chonet's model. And so U will be called the indirect utility because it depends on what the price menu V is. And so about 10 years ago with Alessia Figali and Young-Hyun Kim, we observed that if you strengthen these Ma-Trüdinger-Wang conditions that actually come out of the regularity theory for the Monch-Kantorowicz transportation problem, well, it's a very interesting, so an interesting question about this problem is, is the monopolist maximization problem a convex function of either V or U? And I don't know how to address whether it's convex in V or not, but I can tell you when it's convex in U. And it turns out to depend very sensitively on the choice of benefit function. And in fact, the bilinear function of Roche and Chonet is kind of on the boundary of benefit functions for which the principal's problem is, or the monopolist problem is convex. And oh yeah, I should have said the economic lingo for these kind of asymmetric information problems where you have a single party on one side of the market and a large number of parties on the other they're called principal agent problems. So in this case, the monopolist would be the principal and the potential buyers or shoppers or consumers would be the agents. And of course, very interesting, when you have a convex problem, you have good numerical algorithms, gradient descent or whatever for finding the solution, and you also have nice theory. So it's relatively easy to characterize the minimizer using Kuhn-Tucker conditions, Kuhn-Tucker type conditions, and it's maybe to show uniqueness and maybe to show stability. So if you perturb a convex problem, the minimum is not going to move too far away, provided you perturb it in such a way that you respect the convexity of the problem. So somehow for us, this question of whether or not it was convex was a very a central question, and we show that some strengthening of these Ma-Trüdinger-Wang conditions is sufficient to guarantee the convexity and also necessary. So in parallel with Zhang's thesis, two economists, Noldeke and Samuelson, gave an existence result moving beyond the quasi-linear model to direct utilities, which can depend on a non-linear way on price. And I should also mention that regarding the work in progress, there's another related problem, which is a problem in mechanism design where you're trying to auction off goods to a field of potential buyers, and they all have different valuations for the good, or maybe probability measures for how likely they are to value the good highly. And you'd like to figure out an optimal auction mechanism. And this, for a single good, this was worked out by Roger Myerson in the early 1980s, 40 years ago. And if you're trying to auction several goods at once, then there's a duality principle discovered by Daskalakis and collaborators 5 years ago that in a way inspired our work. Okay, so any questions? So now let me describe the hypothesis that I'm going to model this under. So I'm always going to assume that my direct utility function is continuously differentiable, and I need the space of potential buyers to be at least as large as the space of products being consumed. And then for every pair of buyer types, I'm going to assume that if you look at the one jet, so the value of the direct utility and its gradient with respect to x, that gives a one-to-one mapping, continuous mapping on the space of product price pairs. And let me call the inverse to the mapping y bar. So, and I want the range of that mapping, so the set of all the one jet as the product price pairs range over all possible values to be convex. And now here's the crucial condition for us is going to, the crucial definitions are coming up here. So I want to look at curves in this, for a given buyer type, I want to look at curves in the product price space. And I'm going to call such a curve a G segment if its image under this nonlinear mapping is an affinely parameterized line segment. And the crucial assumption is going to be if you look at any G segment and then you change the buyer type, but you look at that path in the product price space. So of course, if x naught equals x, then as part of this definition, G is going to be an affine linear function of t. And now I want that if I perturb x naught away from x, that it becomes convex, and moreover that it's not only locally stays convex, but even for global perturbations of x naught relative to x, I want the direct utility to be a convex function of t. So that's going to be my hypothesis G3. And I should say just that this generalization to utilities that depend non-linearly on the price is strongly analogous to what Trudinger called generated Jacobian equations, which were first investigated in the context of the designing mirrors or lenses that take a given incoming light distribution and produce a given outgoing light distribution. So that's sometimes called the reflector or refractor antenna problem. And if you're doing everything at a large distance, you don't need then G becomes linearly in the Z variable. But if you're not so far away from the mirror and the lens, then you need these nonlinear G's. I guess this was also relevant to the design of what do you call it? Progressive lenses for contacts. So Kobe Rubinstein and Gershon Wolanski in Israel, I think, had a company that did progressive lenses for contacts or for glasses, prescription glasses, and it was based on using these kind of generated Jacobian equations. Okay, and the rest of the hypotheses are kind of innocuous, I think. We're going to assume that nobody likes to pay higher prices, so there's some monotonicity in Z. And if you raise prices high enough, you can price any buyer out of the market. And finally, that the profits, the monopolist's profits, are going to be a continuous function of all of their variables. Any questions about the hypotheses? Okay, so here's the reformulation of the monopolist problem in terms of the buyer's indirect utility. So the price menu V leads to an indirect utility U that you get by computing this maximum over potential products that they can buy. And since U minus G is non-negative, with equality at the product that actually attains this maximum, you get some first order conditions satisfied, which say that both U and its derivative with respect to X agree with G and its derivative with respect to X when you evaluate at the product selected. And because the mapping from the price product pairs to the U du pairs is invertible, that was hypothesis G1, you can identify the product and the price selected in terms of the indirect utility and its derivative, and the inverse map to the homeomorphism from 1. And so you can re-express the monopolist's profits as a functional of U instead of V. So this should be pi rather than G. That's a typo. So I average over the different agent potential buyer types. My profits depend on the buyer type and the product selected and the price they paid, and both of those pieces of information. So Y bar is basically Y comma Z are encoded in Y bar. And the point is that this Y bar of G is some known function and it depends on the U and its gradient. And so you want to maximize this functional here over all U, which arise from some price menu V. And those guys, U's that arise from a price menu V, are called G convex U. And of course, they also have to be bigger than the reservation utility that the consumer would get by choosing the zero product for zero price. All right. And so here I'm starting to state the first results now. This maximization over G convex functions U of pi is, there's enough compactness in the space of G convex functions U and continuity in the dependence of pi on U in order to know the maximum is attained. You don't need G3 for that, or G2 for that matter. And moreover, the map between, as long as the distribution of agent types is absolutely continuous with respect to Lebesgue measure, the map that takes an agent type X to the product price pair that he or she selects is given by Y bar G composed with U and its gradient.
By the way, once you get U, let's say you maximize and you get U,
yes, is
there any transformation that takes you back to V?
Yeah, okay. So that's a good question. It's very much like a convex duality. So if you take a function and you compute its Legendre-Fenkel transform, you get a convex function, dual. If you compute the Legendre-Fenkel transform of that, you get another convex function. And it's in fact the convex hull of the original V.
Okay.
So you can't recover V, but you can recover its G convex hull.
Okay.
And if you're willing, and it turns out that any outcome that you can achieve with a V is also achieved by its V convex hull. So if you're willing to restrict your attention to price menus that are G convex, then which doesn't cost generality in terms of who's going to buy what, then you can recover V from U. Yes. Other questions? Okay. And okay, so yeah, here's this first kind of crucial theorem for me, which is that assuming all of these other hypotheses, I want to know if the problem is convex. So first of all, I would like the domain to be convex, and then I would like the problem that the objective to be I'm maximizing. So I'd like the objective to be concave on a convex domain. So is the domain convex? Well, the domain, the set of functions U that can arise as the G transform of a V is itself a convex set if and only if G3 holds. So G3, which was the convexity of the direct utility for a different type of agent along a G segment for a given type of agent, is a necessary and sufficient condition for convexity of the domain. And once you have convexity of the domain, things are fairly simple. The objective you're trying to maximize is concave on that domain if and only if the integrand is concave on every G segment. And here, I don't need to put x naught, it's the x for which this y and t actually form a G segment. And it's not so interesting to maximize convex functions, although I guess that at least if you were maximizing a convex function instead on a convex domain instead of a concave function, you'd know the maximum is attained at an extreme point. But this theorem too is very robust. So if you change convex to concave here, concave to convex, you can change convex to concave here. So. And of course, if you want, convexity is great. Strict convexity even better because it tells you uniqueness of the maximizing U, or strict concavity. If you want to improve this concavity to strict concavity, then you need to assume some kind of either uniform concavity of pi, then you get a necessary and sufficient condition for uniform concavity of its average over the different consumer types. And for the uniform convexity, you want to use a Sobolev norm to measure the distance between direct utilities. I guess this is a homogeneous Sobolev norm. And if you just want a one-way implication, then strict concavity of this along G segments implies strict concavity of the capital pi among U. And in either of these cases, you get uniqueness of the optimal strategy and you get stability in the sense that if you have a sequence of data which converge to some limiting data in an appropriate topology, then not only will the limiting solution be unique, but the sequence of approximate solutions will converge to it uniformly with respect to the limiting measure of products consumed. Rather with respect to the limiting measure of agent distribution. So my message about stability somehow is that if you perturb Roche and Chenet's example in such a way that you respect convexity, then yes, your solution is going to be stable with respect to perturbations. If you perturb it in such a way that you violate convexity, all bets are off. And I should reiterate that the case GXY, the case studied by Roche-Chenet, which is this one, is actually kind of borderline because this crucial hypothesis G3 in this theorem above, when you're asking for convexity along G segments, for this bilinear surplus, the G segments are just line segments. And the convexity, the thing that you're wanting to be convex is just linear. And so that's somehow why you're in a borderline case. And if you want examples of things that are non-borderline, you can get them by perturbing Roche and Chenet's example by a product of a function of the agent type and a function of the product type. And as long as these functions are not too large, so if they have a bound of 1 on their Lipschitz constants, then if the first function is convex, you need the second function to be convex if you want to respect to B3, and that's if and only if. So somehow, if the agents and products lived on convex graphs, then you would be respecting G3. But if the agents lived on a convex graph and the product types lived on a saddle or a concave graph, then you'd be violating G3. And I think that, okay, so I have time to talk a little bit about the proofs of these theorems, but I maybe don't want to say too much here. And so somehow the crucial theorem had to do with convexity of the space of indirect utilities, of U's that could arise from a price span UV. And so how do you show something like that's convex? Well, if you have two indirect utilities that arise from price span U's V1 and V2, one of the consequences of that is that the first function is dominates, this would be the price paid for the product Y, and if Y is for every X naught, there would be some Y naught and Z naught such that you can produce equality here. And the same thing would be true for a function U1. Given X naught, you'd be able to find the product selected. If facing price span UV1, you'd be able to find the product Y1 selected. And so you'd have a lower bound of the form G for U1 with equality holding at X naught. And then the question is, can you do the same for the average of these two things? Can you find a Y and a Z such that the average is dominated by G of, let's say, Y1/2, Z1/2 with equality at X naught? And there's not too many choices for how you can choose the Y1/2 Z. So if you think about the case of a convex function, you have one lower bound for it and another lower bound for it, and you want to sort of rotate one slope to the other slope. There's only one way you can rotate these lower bounds through the space of affine functions and still stay below your convex function. So you add these two things together, and of course, since U0 is bigger than G at this point and U1 is bigger than G at that point, and now you'd like to have this average dominating something like this, and G3 was just exactly saying that along G segments, you can expect this average to dominate something like this. That was exact, no matter what X you put in here, and with equality holding for the original point X naught. So that was originally what G3 did, exactly what G3 did for us. And the converse, G3 provides the Y1/2, Z1/2. It says that they have to lie in the line segment joining what you got for Y0, Z0, and Y1, Z1 with the given X naught. And the converse is pretty straightforward. If you, so somehow this is the tricky direction, and the converse direction is that if this was violated, if G3 is violated, then there's basically no way you can choose Y1/2 and Z1/2 to get this inequality and still have saturation at X naught. All right. And similarly, so that's somehow the hard theorem, and the easy theorem is this: when is the objective concave? Because the objective was something like integral of this against a positive measure. And so then if the integrand is concave, then the integral is concave. And the objective was of the form profits of X given choice Y, and we know how Y depends on U. And so if I interpolate linearly in the space of U, and I assume for each X that this is concave, then the integral is concave. And you could quantify that concavity in a fairly straightforward way. And similarly, if the concavity this was violated at some X, then you would just choose a measure mu, which concentrated all of its mass near that X, and you get a contradiction of the concavity of this fellow. Questions? Great. So if not, let me switch to the second part of the talk, second half of the talk. Oh yeah, sorry. So I have a little bit of, maybe it's also interesting to know that although I presented G3 in this very kind of pedestrian manner, there's actually some differential geometric content in it. So at least in the case where the dimensions are equal of the space of products and consumers, of course, when you look at product price pairs, you've now made them unequal. So let me introduce a dummy variable X naught to restore the symmetry. And let me extend G by multiplying the original G times the dummy parameter X naught. And I need to make, in order to have this differential geometric interpretation, I need to make a few more hypotheses. Like I want the the n plus 1 by n plus 1 matrix of mixed partials to have non-zero determinant. And I want that when I, G was a monotone function of price. When I invert that monotone function of price, I want to get another functional that satisfies all the hypotheses of that I required of G. And if all of that is true, then G3 becomes equivalent to a sign on the mixed fourth order derivatives of capital of the extended guy with respect to two derivatives in the x variable and two derivatives in the y variable along two curves, at least one of which has to be a G segment with respect to the point where I'm taking derivative on the other one, S naught. And okay, so that looks a little funny, but in Riemannian geometry, if you have a triangle, arc length parameterized geodesics, x of s, y, and t passing through the same point, x naught equals y naught, then the sectional curvature of such a triangle in a Riemannian manifold measures the length of separation between xs and yt. And in fact, you look at the distance between xs and yt is to second order and st Euclidean. And to fourth order, the only non-zero correction involves this mixed fourth order derivative of, let's say, the Riemannian distance squared. So maybe it's not so surprising to see curvatures come up in this context. And so here's my one slide devoted to differential geometry. So, so if I look at the space of agent types cross the real line and product price pairs, that's a 2n plus 2-dimensional space. And if I can think of the mixed derivatives of G and their adjoint as giving, because this is assumed to have non-zero determinant, I can think of that as giving you a metric tensor on this space, but it won't be positive definite. It will have the same number of positive and negative eigenvalues. And what is the convexity G2? It's basically asking that for every horizontal coordinate, the horizontal fiber is n plus 1-dimensional fiber is geodesically convex with respect to this metric. And for every vertical coordinate, the vertical n plus 1-dimensional fiber is geodesically convex. What is hypothesis G3? It's asking that when you choose a horizontal and a vertical vector, the sectional curvature of the two planes spanned by this horizontal and vertical vector in this metric is non-negative. And somehow it was surprising for us to see this sort of pseudo-Riemannian geometry coming up in the context of this economic problem, but it's coming up for the same reason that it comes up in Einstein's theory of relativity, which I'm going to talk about next week a little bit. And the idea is somehow if I parameterize, a different observer could parameterize the automobile types and the agent types differently. But if the optimization problem has a unique solution, it should have the solution, the question of whether or not it has a unique solution, it should be independent of how I choose to parameterize the automobile types and how you choose to parameterize the agent types. And that sort of diffeomorphism independence of the problem tells you that questions about like whether it has a unique solution or not ought to be answered in terms of invariant quantities. Like there aren't that many invariant quantities, so curvatures are one of them. Okay. So now let me move, in my last 10 minutes, let me move into the second part of the talk. So I want to come back to the square example of Roche and Chonet. So because they're dealing with this bilinear preference function, the profits that they're trying to maximize are this one, and they're trying to maximize it over the space of convex functions. So U, because for every y, this is an affine function of x, so U is a convex function. It's also non-negative. I think they took their y to be the positive orthant, so it also has non-negative derivatives, but I won't worry about that. And so our duality says that the profit maximization studied by Roche and Chonet is actually equivalent to some dual minimization. And here they assume the cost to the agent of producing product type y is going to be some function c, and what appears in the dual formulation is the Legendre transform of that cost function C. But it's minimized over this very strange set. And on the next page, I try to interpret this set. So basically, the monopolist maximum profit coincides. So this problem here is like the net, it produces the net value for a co-op, which is able to offer its members goods Y at prices cost to the co-op, so at price C. But you're minimizing over distributions S that satisfy this very strange constraint, which basically says that if members whose true type is S display irrational behavior and select a product as if their fake type was X, then the expected gross, then the gross value of the resulting assignment grad U of X to those co-op members dominates the monopolist's expected gross revenue. So this is the monopolist's expected gross revenue, and this is the value of the co-op to the members whose true type is SX. And so one of these inequalities is pretty clear. So this, if this holds, I can replace this term here by Sx dot grad U, and then the definition of C star, the Legendre transform, tells me that Sx dot grad U minus C is less than C star composed with S. And the reverse inequality is the usual kind of convex duality a la Rockefeller-Rochonnet. It's sort of a saddle argument, and I probably don't have time to do it justice. But what's the point? The point, you're trying to compute this profit maximization. You introduce some Lagrange multipliers, probably T. There's some dual minimization, which comes out of the definition that relates C to C star, this infimum, and you want it, and of course, so if I look at functions S that are of the form T composed with grad U, that's a special subclass. So if I replace that with some general function S, this can only go down, and I'd like to interchange the infimum with the supremum. And because I can always do that, giving an inequality, but because the thing that I'm trying to find the saddle point here of is a convex function of S, because C star is convex, and a linear function of U, von Neumann's minimax principle says that I can interchange if there's enough compactness, I can interchange the inf soup without producing a gap. And after you interchange the order of the inf in the soup, you get the dual problem out. All right. And so now let me return to the square example of Roche and Chonet that I described at the outset, and the bunching that they found. So, and that was for the special choice of costs, C is 1/2 y squared. Basically, if you apply calculus of variations to the subjective functional, you're trying to maximize this overall non-negative convex U. Then depending on the rank of the Hessian of U, where the Hessian has rank 2 on this square, it's an unconstrained optimization problem, and this is very much like minimizing a Dirichlet energy. And so you should expect something like this part linear in U, so you should expect something like Poisson's equation to come out. Of course, where the non-negativity constraints binds, U0 is going to be 0. That's the rank 0 part. And in the intermediate region, omega 1, where the Hessian has rank 1, you can only perturb U in one direction. You can only perturb it along the diagonal, not orthogonal to the diagonal. And so instead of getting a PDE, you get an ODE. And if you make the assumption that U is this kind of symmetric function of x1 plus x2, so that it depends only on where I am along the diagonal, then the ODE basically gives you the form of that function K. And the boundary conditions are that both the value of the function and its gradient has to agree with the 0 function at the lower boundary. And so, as I was saying, in the uniformly convex region, you get a partial differential equation. It's a Poisson equation. Now it's subject to boundary conditions, and they turn out to be Neumann conditions. But on the other hand, according to this unpublished result of Caffarelli and Lyons, both the value of the function and the value of its normal derivative have to agree at the lower boundary. And so it becomes an overdetermined problem. So you have kind of this, on part of the boundary, the part where the rank 1 region intersects the rank 2 region, your problem is overdetermined. And so the solution is not as simple as what Roche and Chonet guessed. So they had sort of heuristic and numerical arguments in support of their solution, but more careful numerics done about 5 years ago by Jean-Marie Mirbeau showed that the rank 1 region is not a strip. It actually has a non-trivial boundary behavior. And the set of products consumed is not a square, but in fact, there's a one-dimensional part here, and there's also 2 one-dimensional measures on the boundary of this green region of products consumed as well. And so what we're able to do using the duality that I just described is give what we believe is an analytic description of this boundary and these measures. And that's what I'll try to do in the last few minutes, describe for you. So the claim is that the region, the rank 1 region, splits into 2 pieces, and there'll be a symmetric piece over here. One piece where the iso choice curves are indeed anti-diagonal, and one piece where they start to rotate. So I call them omega 1 0 and omega 1 plus, and this would be omega 1 minus over here. And so what we want to describe is a new system of ordinary differential equations on the region omega 1 plus and omega 1 minus that say how the indirect utility, which has to be affine along each of these isochoice curves, but it's still going to depend on the angle of the curve and how long the curve is. And that you then marry this, the question of how long these segments are, so where the boundary of omega 1 plus and minus fall, determines the region omega 2. And there's a free boundary problem that allows, by varying that boundary, you can satisfy both the Neumann and the Dirichlet conditions on the Roche-Chenet Poisson PDE. Okay. And so let me try to write down what this ODE is. Here's the picture. As a function of angle theta with the horizontal, I'm going to need sort of the length of this curve, call it R, and also the height h at which it intersects the diagonal. And then if I call R the distance along the segment of length capital R of theta, U plus 1 has to be, as I said, an affine function of where I am along that line. And so it's given by some function m of theta times R plus an offset b. And it turns out that if you're willing to choose R a priori, then m is determined by trying to solve this quadratic ordinary differential equation subject to these boundary conditions at the lower boundary on the value and derivative of m. And that, of course, that depends on the solution on omega 0, k, that we already wrote down. And once you solve this equation for m, you can recover the height and the offset b just by quadratures, by doing integrals. But of course, everything depends on knowing R, and R is determined by a free boundary problem. So, and if you imagine, for example, that you fix the Lipschitz R, then you can solve the, let's say, the Neumann problem on omega 2, and then you can ask, is the Dirichlet problem really solved or not? And then the idea would be to vary R until solving the Neumann problem also solves the Dirichlet problem. And we assume that such a choice exists, so we don't have a rigorous proof for that. But if you assume that such a choice exists, then you plug the whole solution, the ODE that I just showed you, and the two ODEs and the PDE and the boundary conditions into our duality principle, and then you find that such a choice optimizes. Now, why do we think such a choice should exist? Well, basically, if we already know an optimizer exists and is unique and fairly smooth, and if the sets where its Hessian is rank 0, 1, and 2 are smooth enough and really have the topology that I described in the picture, so omega 1 has the expected 3 components, then this solution would give you those choices. And what could go wrong is maybe omega 1 actually has 5 components, and the other 2 are so small you don't see them in numerics, or maybe omega 0 has extra components that you don't see in numerics. So we doubt that that's the case, but we don't have any rigorous argument to rule it out. All right, so I think I've basically come to the end of my talk. I have a slide of conclusions. So the conclusions for the first half of the talk are that basically whenever you have convexity or concavity in an optimization problem, that's a powerful tool both from the numerical and theoretical point of view for addressing things like uniqueness and stability and characterizing the optimum. And under this duality between the price menu and the indirect utility to agents, we're able to give necessary and sufficient conditions for convexity of the monopolist problem. And those are related to curvature conditions governing regularity and generated Jacobian equations. but we're able to adapt those conditions to payoffs that depend nonlinear on the price paid. And we have proposed a new duality that certifies solutions in the quasi-linear case. And we've discovered that correcting Rochet's solution to the square example requires solving an unexpected free boundary problem. And so that's where I would like to leave it. Thank you very much.
Thank you for that. Any question?